Good afternoon, everyone. Welcome to the December edition of Innovation Insights. It's amazing that the year has gone by as quickly as it has. So we're at the end of 2024 and looking forward to a great 2025. So thank all of you for joining us today here at the end of the year. We've had 11 of these presentations this year. The only month we missed was the month of our annual members meeting, which is just a tradition that we do. We skip that month. But just before I introduce our first speaker, I just want to go over a couple things about IACMI, about our offering to members around the themes of convene, connect, and catalyze. The open access facilities, the co-funding that's available through various streams, the opportunity for networking, working on projects, our fantastic working groups that give you a place to come together with others, and other offerings we have around interns and education. So if you are not yet an IACMI member, here's how you join. It's iacmi.org/members. Fill out the request form there, and we will get back to you about the next steps in the process. Just a little reminder, as we go into 2025, that will be our 10th anniversary year of IACMI since its founding in 2015. And our members meeting will be in the middle of the year in Dayton, Ohio. Should be a great time there, recapping a lot of what has happened over the first 10 years of IACMI and looking forward to what we're going to be doing in the future years of IACMI. Just to let everybody know that today's webinar is being recorded. They're all stored on the IACMI website. So if for some reason you don't, you or a colleague want to go back and look at what was said today, catch back up on that, within a few days this presentation will be uploaded there. And then even those folks that might have registered for today but got caught up in another meeting or something, they will all get a reminder that it's available to go see as well. So we've featured over 100 members and partners in our 30 episodes since May of 2021. And I'm going to make a pitch right now for our January edition. We've got that lined up. We have two professors from Vanderbilt University that are going to talk about digital twins for process control, but then we're going to lead into a feature presentation from Joe Fox, who's the president of FX Consulting, and has worked with us on an IACMI project called Project Impact that recaps the first 10 years of IACMI. So it's going to be, pretty interesting presentation on some of the things we've learned from our members and others as we've gone through this year, trying to understand how IACMI has impacted the composites landscape across the country and the world. So today we have three great presentations from small companies, and I really like the mix today because we talk about manufacturing of parts, inspection of parts, and novel design of materials, and these are all cool things that come together to move the industry forward. So I know that a lot of our large companies pay attention to what's going on with IACMI small companies to discover new ideas, and I'm really looking forward to seeing what's going on today. We will have, if you have questions during the presentations, we'll try to get to them as many as we can, post them in either the Q&A or the chat function, and we will answer as many as we can. And if we switch speakers and there's still lagging questions, we'll ask those speakers to continue to answer those, through the chat function. So with that, I would like to invite Bill Dykstra, who's the president of Temper Incorporated, to load up his presentation, and let's get going.
All right.
Stop sharing there. So Bill, if you want to start sharing your presentation. Just put it in slideshow mode and we'll be good to go.
Okay, so we're going to be talking about induction heating for mass producing components. So just a little bit of background and propaganda. So our vision is to change the way materials are processed using magnetic fields, and those magnetic fields are induction heating. Obviously, our Temper management team is Dr. Bonnie, myself, and Luke. Our core competencies are smart susceptors. We've been using induction heating for the last 25 years. 27 years now. And specifically applying that to smart susceptor applications for the past 18 years. You've got some products with significant sales, that section, and we did have a couple of SBIRs. However, neither one of those SBIRs were in composites. Patents, there's a bunch of them, and these are, we've been basically developing this technology for Boeing for their 757 replacement plane that was canceled in the year 2020. We went to Boeing intellectual property and we said, we'd like to make, use, and sell the technology that we've been developing for you. And they said, yes. So we've got licensing to these 86 patents, plus we own an additional 18. These are not patent pending. These are issued patents. For those that are unfamiliar with induction heating, this is a really simple analysis. Basically, if you went back to the 3rd grade and you said, I made a magnet using a battery, right? Now, in the second case, if I take and I switch the polarity of the battery back and forth several times, I create a magnetic field at one end. Now, when I replace the DC power supply with the AC power supply, now I generate the heat based upon the, just a minute here, I gotta shrink this little box down. Based upon the electron flow, now if I take and I hollow out the nail and I make it into a shell, I now have a magnetic field that induces a current into the shell, and then that generates heat, and then the heat is transferred to the part. What makes a susceptor, or that material that the magnetic field couples into a smart susceptor, is that we take and make the Curie temperature of the material, or that temperature where all ferromagnetic materials become non-magnetic, to the temperature that we want it to become non-magnetic at, or where we want it to stop heating. So as you can see here, in the lower left-hand corner, all of these magnetic, this is a traditional resistive heating type of methodology, where you might have a thin section of the tool heats up very quickly, and then the thick area where there's a big heat sink, it heats up slowly. With the smart susceptor process, it just goes up and it flatlines, right? And so the chemical composition of the material is probably the most important. Then you have the reference depth of the induction heating, frequency of the field, and you also have the thickness of the material, are all elements that become a smart susceptor. So you say, well, why is this important? So in the case of a heating blanket, for instance, a traditional heating blanket, you end up putting a certain amount of heat into the let's say a part, and I got a thick area of the part, and I got thin areas of the part. And so what happens is the heat continues, but in order to get this thick area up to temperature, you've got to continue to heat it, which gives you overheating at the edges. With a smart susceptor heating blanket, it starts to approach its Curie temperature, and we end up with even heating. Now, to dig a little bit deeper, and this is as far as we're going to go here, into how it works. It's relative permeability, which changes with the field density and with temperature. So for instance, here, in this example, this is a material that's going to become non-magnetic at, say, 780 degrees. What happens is it's not magic, it's just physics. And so what would happen here in this case, let's say you had a tool with a heat sink. The heat sink would continue to heat here, And where it was thin or where there was not much of a heat sink in the material that's absorbing the heat, it would stop heating here. And so you would end up with this range. And to get more into that, it'll take some more time. So we're going to keep moving on. So what we've made is we make blankets, we make tools for high volume, we make low volume tools. We do some welding, and we have some out of autoclave tooling configurations that we can show you. We've made lots of different parts. This part, for instance, this seat back was made in 3.5 minutes. We've done PPS with polypropylene. We've done PEEK. This part here is 5 feet tall and 15 feet long. It's a 1/2 inch thick, or it ranges from 1/4 to a 1/2 inch thick. We've done bonding and co-bonding. We've done this blanket here, which we'll see a little bit later. This is 9 feet wide, 39 feet long. You can see the other hand here. And then you can see the reusable vacuum membrane on the top and the thermocouples. Again, you'll see this again. We've done portable heating solutions. We have a reversible repair patch for aircraft. A patch that can be literally applied to a plane, let's say for frac damage, in less than 10 minutes, and we can reverse the bonding process in less than 1 minute. And then we also do welding. All of the equipment that we've needed over the years, we've had to design, build, have somebody else do the machining, and then bring it out and build it ourselves. None of the equipment we've ever done has been supplied by anyone because it's so specialized. So again, we're going to talk about matched metal tooling, ceramic tooling, blanket heating, welding, and this reversible temporary repair patch. So again, if I look at this from the physics standpoint and where we started, you have an induction heating field that is supplied via a coil, and you can see all of the different connectors for the coils here onto a shell, and then the shell heats in under 30 seconds, and you can see that 30 seconds here, and on these it's a real eye strain, but yeah. And then it's supported by a rib pack, and then it's cooled via compressed air, which gives you a very quick drop. We're in the 400 to 500 degrees per minute on the cooling, and 400 to 500 degrees, or actually 600 to 700 degrees on the ramp. We've done a lot of studies on density, repeatability, but whenever we went to sell this particular concept to people, what would happen is you had to purchase the entire tool, which included the coil and the shoe and everything else. So the idea was, hey, why don't we just disconnect the shell from the rest of the tool, and then that brings the cost down. And so we did that with this idea, which was this B pillar. This is the tool that we built, or that we actually modified from another use case. Then we put the insert, we built the insert, we put it inside the tool, and here's the part, and Dr. Bonnie's holding on to it. In the loop condition, you can take these, this is a ceramic tool, and this is what made this part here. This tool is made in 3 modular sections for the lower half and 3 modular sections for the upper half. And the restraint here is also built in a modular form. So from the simplest case, this was 15 feet long. We could go out to 35 feet long, easy enough, by just adding more modular sections onto the restraint and make it as long or wide as we needed. This type of pourable ceramic tooling for low volume also works for this bonding and co-bonding. So in the co-bonding from the previous slide where you saw the part standing up, we used an aluminum air bladder, which works really nicely for positioning the stiffening features in the tool, and also for the quality of the part. We also made a part that was 2 inches thick, and we did this for the Army. In addition, we have some additional concepts. You could use the same concept with, let's say, a tool that slides in and out of a coil that is open and closed, like a clamshell that goes into an autoclave. You could, if you wanted to use it strictly out of autoclave, you could take and put the coil, slide the coil inside the autoclave, or you could use directly heating the coil from the backside of the tool. So there's lots of different concepts going forward. Now we're going to switch to blankets, and this is a little bit better shot of the blanket that we built for Boeing. This blanket has 16 of these individual heating units. Here you can see both sides at our facility under construction. This blanket has been running now for going on 7 years at Boeing's West Jordan facility in Utah. But just to give you an idea of how this science works, in this case, instead of having the coil going around the part, now we have the current going through a Litz wire with individual smart susceptor wires turned around the wire. And so what that does for you is it gives you, again, this very even heating. In this case here, this is a chart. I know it's a real eye strain, but I've got 156 thermocouples that are all working together on this blanket for debulking. And here you can see the reusable vacuum membrane, and you can see the thermocouples all placed into the top. Some of these thermocouples are on top of the rib. It's on a Janicki caul. So we know what Janicki cauls are like. They're a 1/2 inch thick. They got 1/2 inch ribs. Some of the thermocouples are placed directly on top of that rib, on top of the thickest area of the part. And some of those thermocouples are placed on the thinnest area of the part. Again, this is an individual blanket. You can see how even it goes up and how it flatlines. Blankets come in lots of different configurations. This is the portable unit that we have. The temperature profile where you have the 145, 250, 350 degree range. Blankets can be made with a zigzag pattern so that they're very flexible. You can make them like fingers if you had a bunch of pie joints, different configurations. They can be molded into different shapes. And in this case here, this blanket is actually 18 inches wide and 30 feet long. We also taken the technology and we've adapted it to welding. So in this case, we've got smart susceptor wires. These wires can be coated so that corrosion, it becomes a non-issue. These wires are embedded inside of PEEK resin, and these are 2 PEEK parts that were welded together. This part here, this is a PEEK part with carbon fiber. This the brown part down here at the bottom was PEEK with fiberglass, and you can see the weld. And for instance, if you wanted to weld in space, you could take this bracket, you could pre-put these little patches onto the bottom of it and use a robot to weld it together. And as you can see here, it flash heats. So the wires get very hot, very fast, like in 3 seconds. And what that does is that heats the wires, melts the resin, but doesn't disturb the fibers. You can see here, the fibers are undisturbed. We also took that to a new level, and recently came up with a repair patch. So this repair patch concept uses either a thermoplastic or thermoset, but in the simplest form, it would be a thermoset. And let's say that the thermoset was triggered to a 250-degree temperature range for the resin. The smart susceptor on the backside would be with say 275 degrees. So in the simplest case, I'm going to take this blanket, I'm going to put it over top of the patch, and I'm going to take my stainless steel, I'm sorry, we've got a patch assembly that I peel off the back side of the patch and I stick it onto the plane. And then I take my reusable vacuum membrane, which has suction cups on it, and I place that over the top. I then heat the reversible bonded patch to where it conforms to the plane. And then there's a second coil built into the blanket that heats the smart susceptor that then welds the composite patch to the plane. But the key here is the plane could then go out and do whatever number of runs that it needs to do because it's going to have a pressurized cabin. But the key is when the plane goes to the rear, you can literally pop these patches off in less than a minute. And the reason why we know that is we're currently developing this for another customer. Anyway, enough said there. Okay, so to us, the world is full of nails, and we just have a hammer that every time that we look at a different application, we say, hey, we can do that. So, questions?
Thanks, Bill. So I'd ask people to put some into the chat or the Q&A. For some reason I'm not seeing the Q&A at the moment. But what I would one question, quick question before we move on to the next speaker is tooling considerations. Do you have any restrictions with respect to being able to use composite tools, magnetic tools, non-magnetic tools, or or magnetic receptors?
Well, in the case of the blankets,
for example, do you need? Yeah.
Okay, so in the case of using a blanket to heat the tool, an NVAR tool is the preferred way of making that call, right? And so it could be NVAR, it could be nickel, it could be whatever, because you're not directly heating that tool. In the case of trying to make the tool out of let's say nickel, right? And so I'm trying to make the tool out of nickel and I'm trying to directly heat that tool, that won't work. So for instance, NVAR has known Curie temperatures. What we've learned is how to adjust the Curie temperature of that material. And you would think that it would be one way, but it really isn't. There's some elements inside there that if you change them a little bit, it makes a huge difference, which is probably the reason why when other people have tried to do this, they've got sometimes they hit it right on the head, and sometimes they're off by 50, 80 degrees, and they wonder why.
Okay. All right. Well, given the time where we are right now, we need to move on to our next speaker. Okay. So I appreciate that, Bill. And again, if folks have questions, please put them into the webinar chat. So. Okay, so our next speaker is Ryan Spencer. Ryan is the CEO and founder of Thermomatrix. Ryan, as soon as you can go into slideshow mode, you need to switch your screens or perfect. We're good to go. And unmute yourself, please, as you do it.
There we go.
Yeah, but now you need to go back into slideshow mode. So
Yeah. Let me see. And
and,
I'll swap it. Yeah, no, thank you, Dale, for the introduction. And thank you, IACMI, for inviting us to give this presentation. I am Ryan Spencer, CEO and founder of Thermomatrix, where we're providing confident inspection solutions for clean manufacturing. So just for those that aren't aware, what is non-destructive inspection, or also called non-destructive testing or evaluation? It's the methodology of evaluating material properties through, material properties, components, or systems. But the key thing is without damaging them, obviously, non-destructive. And it's a vital tool for manufacturers to support their quality control and quality assurance through their production by supporting defect detection, material characterization, and just that overall quality control. And in general, the NDI market is expected to grow. It's kind of a hot topic. You go to every conference and, just general discussions, and it feels like everybody wants a more reliable, a faster, and cost-effective inspection solution for their bottlenecks within manufacturing. And that's kind of where we're seeing this. There's a lot of traditional methodologies out there that in a lot of cases, they fit the need and they do great and they accelerate. But there are some technologies where they are the bottlenecks, right? They have complexity to them. They're slow with their inspection and maybe even slower with their analysis. And then another thing is costly. A lot of the solutions that are great, they provide amazing results, but there's no way you can actually implement them and be cost effective for total manufacturing inspection. So that's where we step in, and we have a belief system that we believe there is a multi-stage that you should take with your inspection methodology. First stage, let's do a large coverage, large field of view and rapid inspection. See if locations cross a threshold and can kind of highlight hot zones in order to do an initial detection. And then the next thing is then you can go into stage 2, either with our technology or traditional technologies where they provide a localized and high resolution characterization of those defected areas. This kind of brings a balance between, having that rapid inspection and detection, and then also having those fine details and local inspection. So here at Thermomatrix, we have developed a vision inspection solution that we believe will help manufacturers achieve precise, efficient, and sustainable production to overall support their quality control process. We want to position ourselves as a rapid and cost-effective inspection solution to help with those defect detection, help with the material characterization that overall brings high standards for your customers. So what differentiates our technology to ordinary vision inspection systems? So traditionally, you have camera systems, and they just take a snapshot of what's occurring right now. I call this kind of a static image. Usually this is kind of defined for, dimensional analysis or maybe surface, inspection. Where Thermomatrix, where we come in, we actually introduce a heating methodology, and we monitor that thermal expansion and contraction of that material. And now, rather than just dimensional analysis and surface inspection, we have a multitude of capabilities that are through thickness, understanding of your material, and we can provide these main capabilities. directionality of your material properties, thermomechanical response, overall defect detection, and we're trying to crack the code on residual stress monitoring also. To go into some kind of case studies and examples, for the structural directionality capability, one example is within the composite industry, which IACMI is familiar with, is monitoring fiber direction. And we can relate to a pseudo fiber direction from our inspection measurement. And this supports for woven structures or non-woven, discontinuous materials. And we're also material agnostic too. So it doesn't matter if it's carbon fiber, reinforced glass, reinforced. What we're monitoring is that anisotropic thermal expansion that occurs with the fibers. So for our example, we had a non-woven glass reinforced polypropylene composite that was suited for the automotive industry for one of their applications. And we were able to take a 10 by 10 inspection of this component, kind of a full field of view. And we were able to develop a fiber direction map and get a distribution. And that back calculated into the modeling and prediction that was occurring. And we were able to achieve a accuracy of about plus or minus 1.5 degrees of accuracy. And in contrast, the traditional methodology is to utilize X-ray CT, which is a beautiful technology. I call it kind of the top tier technology. But the time it takes to scan one data point and perform the analysis on one data point, we were able to achieve 10x. We were able to provide this full field inspection methodology. So we have a order of magnitudes of rapid inspection that it still falls well within the accuracy of that. Now, again, if you see an area of interest that you want to dive deeper, that's where we suggest, okay, you go into stage 2. Now you bring in X-ray CT to help complement this inspection and have a full understanding. But initially, you can utilize our vision technology as a stage 1 inspection to get full field of view, full coverage of your components. Next one is thermomechanical response. We're actually supporting the semiconductor industry, where we are monitoring local CTE values, coefficient of thermal expansion of this IC package, this microchip. And this was a problem child microchip where it was always thermally fatigued cracking in the corner. So for us, we were able to actually measure and quantify this CTE mismatch that was occurring. We see a large distribution and mismatch in these values, and essentially confirmed why they were seeing this failure mode. And this helped support the R&D and development of this microchip for future production. Another case study is defect detection in general. We're looking to support, delaminations, micro cracking. We're still scratching porosity, but we have an example of monitoring delaminations with an array of simulated defects that are embedded in a CFRP unidirectional composite. And you can see initially, with our heating methodology, we can monitor the 15 and 10 millimeter defects. And once we were able to improve our heating methodology, we can see a more full field of view inspection, actually capture all the way down to 3 by 3 millimeters defects. And again, this is a rapid inspection, rapid heating, rapid inspection to support that large inspection methodology. Another example, we were utilizing our technology to monitor this glass reinforced composite supported for the automotive industry. And we found a micro cracking that was occurring. You could see our heated zone that we were performing heating, and then the high thermal expansion outlined where micro cracking was occurring. And visually, you could not detect this. It wasn't until we applied our heat, you can actually see the cracks open up. And with our vision system was able to rapidly capture this. The last one is residual stress monitoring. This is a kind of universal issue across all areas of manufacturing, not just composites, but traditional metal manufacturing or additive manufacturing where there's high thermal gradients that are occurring and eventually can lead to residual stress cracking. And now we're still in the early stages of developing this technology, but we want to bring again, rapid and large field of view inspection solution that's also cost effective with our camera systems. And we're looking for any industrial partnerships to further pursue these opportunities. So all these case studies, we're utilizing our initial product of a lab scale vision inspection system. This is a R&D material characterization tool that's set up for lab scale. We have a very high pixel resolution system. It is a very modular system that can be adapted to any size of your components. It provides rapid automated inspections that can help with your R&D characterization needs. Now, we are part of a DOE-funded incubator over at Oak Ridge National Laboratory at the Manufacturing Demonstration Facility. We're through the Innovation Crossroads Incubator. This is where we are showcasing a scale-up demonstration piece that we are bringing. So we're going to have a large inspection chamber with a robotic arm for clean automated inspection. And we're going to attach our advanced multi-camera vision system to this. This will provide, again, that rapid, cost-effective solution that we want to demonstrate for use cases. And again, we're open for collaborations once this system is up and running. Now we try to position ourselves to also support in situ monitoring. Our camera systems can be embedded the manufacturing process and will allow that rapid inspection. Specifically within composites, we're trying to go through void content, being able to monitor that, the subsurface delaminations, fiber waviness by monitoring that fiber direction and misdirection, and again, that surface and subsurface microcracking. And we want to provide a closed loop feedback system where we support predictive analysis to help with that closed loop feedback system and really provide a reliable and sustainable manufacturing process. As mentioned, our technology is material agnostic. As long as we're able to monitor that thermal expansion and contraction of your material during this thermal cycling, we're able to provide these capabilities. So again, we're tried and true within supporting a multitude of composite applications, but we're looking at other industries, as mentioned, from semiconductors, DoD applications, to even rail manufacturing and in-service solutions. And now our overall goal is to provide reduced cost, improve efficiency, and overall save lives, to bring high quality, high assurance to to your customers, it ensures that we can bring the safest environment for our customers and for all of society. And IACME has been a great institute to provide support. They've given great guidance and networking opportunities for ThermoMatrix to help us accelerate. So looking forward to reconnecting with anybody interested. I would be happy to discuss any future collaboration opportunities where we can find out where this inspection solution can solve problems. And just want to do a huge shout out to our supporters. We appreciate the support from the Department of Energy, Oak Ridge National Laboratory, Innovation Crossroads, all the way from University of Tennessee, where this technology spun out of, NSF, and again, IACME. They've been great supporters with our development. So we're open for any questions or further discussions. Thank you.
Thanks, Ryan. We need to move on to our next speaker, but so if folks have questions, and put them into the chat or the Q&A box. I've got one, and I will do that as well. So appreciate your presentation today. Thanks.
Thanks, Dale.
If you want to stop sharing, we'll move on to Ben Kent. So Ben Kent is Business Development Government Programs Coordinator for Cambium. It's a materials company. And Ben, I'll let you pull up your presentation, and away we go. And you are on mute, so just so you know.
Thanks for the catch. Okay, great. As long as you can see. Perfect. That's the visual is the most important part, but thanks for the catch.
Sure.
Okay, sounds good. Well, thanks everyone for your time today. I am very eager to tell you more about Cambium. We are a relative newcomer to the Composites Institute, so I look forward to not just sharing our information, but learning more about everyone who's already in the organization and how we can work together. Okay, so fundamentally, what is Cambium? So we are an advanced materials company. So we leverage some machine learning applications and some big data applications to innovate in materials discovery all the way into materials manufacturing. So that includes high temperature composites, which is mostly what I'm going to talk about today to this group. Although if anyone is interested, we do have a separate line of products that are in the directed energy and laser protective field. And I'll go into a little bit more where the connection is there. But our main focus as a company, or excuse me, I'll give a quick more background about our logistics first. So we're a relatively new company. We're a post-Series A startup founded in 2019. We have actually slightly more than 30 employees at this point. We're growing pretty fast. And we are spread across 2 facilities. The majority are in El Segundo, California, so just south of LAX Airport. That is our main manufacturing facility and materials development facility. And we also have a smaller facility in the Mojave Air and Spaceport. So that's about 3 hours north of LA, out in the desert. And for a couple of reasons. So partly that is where some of the nucleus of our company, both in terms of IP and people, came from. Also, it's out in the desert at an experimental test facility, so it's a little bit easier to burn things and create some flashy demonstrations than it is in downtown El Segundo. Our financial status is we are, I would say, roughly half and half investor backed, and then also have about 30 million plus historically in government contracts. That number is actually also increasing rapidly as well. So as I mentioned, so where do we focus as a company? We are primarily concerned with what you can see as a macro trend in this chart. Whereas I'm sure this group knows pretty well, we as an industry, as a society, innovated significantly in the petrochemical space, and composites spun out of petrochemicals, really from the World War II to Cold War era. And in the past 20 to 30 years, that has dropped off significantly, especially in commercial applications, but frankly for defense applications as well. So cambium focuses primarily on what are some of the monomers and some of the additional molecules, additives that we can focus on from the biological universe. So the vast array of biological compounds out there, which contain much more information, much more data than petrochemical sources, but really have not been looked at in a manufacturing context. So cambium really tries to vertically integrate all of this. So as I mentioned, using computational tools, large-scale AI models, we look at the library of biological compounds out there from prior research, from available sources, look at and try to predict which molecules would be beneficial in synthesis into composite manufacturing, composite fabrication, build that out into pilot scale production, and then actually start looking at applications development. So as you can see in the quick image there, and I'll talk about this in a little bit more detail, what you see on either side of that drone is a thin film of a resin that has been set on fire while the drone is flying. And that was the sort of aha moment in the initial research that led to cambium, where the resin that came from a biological source actually had a higher char yield, burned slower, and preserved more of the wing, that side of the drone, than a petrochemically sourced resin. And so that was kind of a dramatic moment for a team of both private sector and Navy researchers who said, okay, there's something here, something worth investigating. So I'm going to, for the purposes of time here today, I'm going to go through each of the composite-focused products in this line. This is just a quick overview of cambium's progress for each of these different product families. So you can see up top, our main focus right now is producing resins and prepreg. So both of these we're focusing on making sure that we can do this in a domestic US-based supply chain. Some of the precursor chemicals, we're not quite there yet, but in terms of going from resin development, synthesis, and then domestically prepregging, that is where we're at currently. We're looking to get to production scale up within the next year, and then I think we are going to be, if I have the dates correct exactly, we're going to leave a low volume exemption and start having a commercially available product in early 2026. So just slightly over a year from today. Down the line, we're looking also into slightly more robust parts. So we're working with a line of developmental processes with the Army, actually, in terms of tow preg. So looking at filament wound structures, tube structures. So go into that in a little bit more detail. I mentioned very early on, I'll gloss over this briefly, but we do have an entire line of directed energy protection that will probably become one of our first commercially available products, interestingly enough. So basically, as I mentioned, looking at that realm of biological compounds, even though the majority of our focus as a company is on molecules that can be integrated into composites manufacturing, we found some of those same molecules react really well to heat and light. And turns out they can actually be integrated into glasses and plastic films that protect against lasers. So completely different industrial process, completely different use case, but just an interesting finding that as you're looking at the realm of biological molecules, you find different properties can be integrated very differently depending on which downstream effect you're going for. And then on as our high level items that we're looking to get out of the lab scale into the prototyping piloting stage in the next coming year or so, we're looking at manufacturing processes using our monomers, using our composites that can produce carbon-carbon material and down the road carbon-carbon parts, potentially at a fraction of what the current manufacturing process costs, and both in terms of time and processing. So the factors that lead to a higher cost for, say, heat shields, thermal protection systems, hypersonic structures, we have initial evidence that we can drop that time of processing and complexity significantly. And in a similar case for high temperature foams. again, using the same monomer basis, but this we're looking at potential applications in sandwich cores, structures, potentially shipbuilding. So we have a little bit of interest from the Navy on that side. Those are much earlier stage, and so as you know, as a point of interest for the Composites Institute, we're also looking for potential collaborators on these lines as well. Okay, so as I've sort of alluded to, we've looked at the realm of biological molecules to produce some of our monomers. Our composites are based on this lovely word phthalonitrile. So a high performance thermosetting resin is our essential first product that we base everything else off of. I'll let you all, I'll leave the slide up for a moment, let you all read some of the details here. Some of the key properties I want to break out here is we're looking at a pretty high temperature resistance, so a TG up there of about 750 degrees Fahrenheit. Fairly high char yield. That was, as I mentioned, one of those early visibly noticeable things about phthalonitrile resin versus a petrochemical source was essentially the visible evidence of a higher char yield, not creating down the road, not creating any sort of oily, smoky, potentially toxic risk factors relative to a phthalonitrile composite, which essentially just creates more char and carbon. And we've also found that it's extremely stable at room temperatures. No refrigerated storage required, so a definite benefit for manufacturing processes down the line there. I'll go into a few more details on the family of products that come out of this, but focusing mostly on neat resin and prepreg at the moment. And yeah, as we've discussed, so you can see a definite world of downstream applications. We're focusing mostly on various high temperature problems. Our team's background and familiarity is primarily aerospace. So a lot of the developmental experiments, a lot of the design behind our process is made with, or those decisions are made with hypersonics in mind, thermoprotective systems, reentry systems in mind. That said, and this may be something of interest to the group, we're very open to inputs from other industries and other use cases. So just as a quick example, one of the areas we're currently exploring with some of our DoD partners is ground vehicles, firewalling systems, things that haven't really been integrated into, say, tactical vehicles in the past because they haven't had batteries and fuels and people and ammo all in the same compartments. And some of the forward-looking design choices behind, how do we use, like, say, hybrid powertrains and stuff. That's an area where composites could be an application in terms of lightweighting and thermal resistance. So that's something we're looking at currently. That's just an example of input from different sectors that we're very open to as we build up this product line. So the next slides are just a little bit more detail on each of those products that I mentioned. Again, I won't hit every single point here, but I'll leave it up for review. This is the prepreg that I mentioned. So we were able to produce the first domestic phthalonitrile prepreg on a commercial production line in the United States. I should add, most phthalonitriles in terms of their development come from, I believe, China and India. And as sort of in the macro national security landscape right now, there's obvious concern about outsourcing too many segments of your supply chain for parts that could be, or for materials that could be downstream go into either defense articles or just critical sectors like commercial aerospace. As I mentioned, so high service temperature, which is true for all these lines of product, as well as room temperature stability. So good for storage, good for long-term storage. We're looking this line for right now. We're looking at a TRL and an MRL of like 5 to 6. I expect this will jump significantly in the next year. But that's not to say that even though this is a little bit farther along than some of our earlier TRL items, we would still be very interested in potential further research or potential further development projects, excuse me, with other members of the institute. So by no means is our entire focus on prepreg a done deal. Moving on briefly, I did mention I think chopreg. So as a related effort, kind of done in parallel with the prepreg, looking at slightly different commercial applications or military applications, primarily in the realm of pressure vessels, military or rocket structures, essentially any sort of like tubular, high pressure, high temperature structure. This is where we're envisioning the toe brake being applicable. As you can see, it has many of the same things that differentiate from traditional composites in terms of the temperature stability, or sorry, temperature resistance and long-term storage stability. This is a bit, again, earlier TRL stage, so we're looking at more like a 3 for both TRL and MRL. Yeah, so as I mentioned, the same thionyl monomer, when done sort of at a lab scale, exhibits a lot of potential in the realm of carbon-carbon. We found that we can achieve similar properties, similar performance goals, using 2 pip cycles in a furnace, relative to what some of the comparator products take like 6-ish cycles to create. So if those properties hold as we scale up, we're looking at like a 50 to 60% reduction in terms of time, intensity, labor costs, etc. All these downstream effects of producing carbon-carbon for heat shields, thermal protection systems, what have you. Again, earlier stage TRL3, MRL2. This is partly a function of our focus on thionyl prepreg right now, as well as just scaling up our own facilities. So this is an area we're definitely eager for collaborators, definitely eager for additional input, both in the research and the manufacturing side, as we look to scale up this capability. Oh, there's a quick video. Very small scale, let's say, torch test of a composite carbon-carbon. Okay. Let's move one more ahead. Okay. And it's similar developmental level, but similar potential for some high impact applications. So this is our foam systems that also comes from that same tree of thionyl monomer applications. Primarily, we're looking at a couple of areas here that are more industrial or military in application, in the sense that a solid composite or carbon-carbon panel might not be the right application. So the foam is a little bit obviously more flexible, able to integrate with different systems. One of the areas we're looking at significantly is protection from electric vehicle fires. This could either be in like a charging facility, or frankly, a lot of problems with shipping. It's a lot of shipboard fire protection systems we've learned are built with oil fires in mind, not necessarily with cargoes of electric vehicles. Or other lithium-ion batteries. Doesn't have to be an EV, but a similar area of concern, where potentially a foam's integrated with a different material or a different composite could be beneficial as a lightweight protective measure. So we've been able to demonstrate the interior chamber protection for a lithium-ion battery box article at some pretty high temperatures for a good duration. So you can see there about 2 minutes at over 2,000 degrees Fahrenheit. Again, we have not explored this in a really robust, methodical way yet, and that's partly our function as a startup, and partly our function as developing this product. So again, if this is of interest to folks in the Composite Institute, we're very eager to get different perspectives on the foam use case, as well as production and developmental scale up. I believe as the last product item. Oh, there we go. And yeah, so I'll pause there, be mindful of time. Happy to answer any other questions. As I mentioned, so Cambium is mostly California based, and we're active in the El Segundo hardware space. That said, we have a lot of partners who are across the country, both in terms of composite or polymer research teams at different universities, and we've engaged with a lot of different DoD entities throughout the country as well. So I say that to say we are not opposed to traveling or shipping samples to collaborators on any point in the country. So thanks for the time, and I'll pause for any questions.
Thanks for that. Quick question. One is, what's the cure temperature and cycle time to cure this? I didn't see that. Or maybe I missed it somewhere.
Yeah, that's a great question. I can get you that info because it's going to depend a bit on the it's going to depend a bit on the substrate as well as it's going to depend a little bit on the application. So that's one of those items where if you're looking at prepreg or if you're looking at topreg, we have a little bit of a different process. We
Mhm.
are sorry, go ahead. Yeah.
No, I was just trying to understand whether it fits in this kind of in the class of 250, 350, 500 degree cure. What? I mean, is there a nominal
Oh, gotcha.
range?
Yes. Yes, so I'm gonna have to pause there on this line. So we
Mhm.
are under an R&D exemption right now from the EPA. So as you see, we have a data sheet date of like the end of this
Mhm.
year and beginning of next year, depending on the timeline. That's where we'll be able to publish open source an entire spec sheet on each of our resin, our prepreg, and each of these
Mhm.
items. I can bring you guys in on one-on-one discussions with our engineers for specific use cases, but I don't have an order of magnitude cure temperature for each one.
Okay. So one of our audiences has asked, phthalonitrile is known for microcracking issues in composites. What are the differences
Yes.
for yours compared to other polyamides?
Yes. Okay. Great question. So, this is where a lot of our collaborators come in terms of mechanical testing, as well as we do a lot of thermal testing in-house, but we also parallel track that with some of our collaborators as well. And that includes both DoD labs, universities, and CMOs. So one of those issues that we're trying to get after is the microcracking. We've found progress in that front under a DoD funded line. And so one of those things that I hope to share within, the next quarter or so, is a baseline comparator against things like polyimide or BMI.
Okay. Thanks. All right. So I'm sure, yeah, folks will be able to reach out to us and get in contact with you
Yep.
for further questions. Very interesting. All right. So that takes us to the top of the hour and the end of this month's Innovation Insights. I want to thank Bill, Ryan, and Ben for their excellent presentations, and wish all of you, you know, happy holidays. And we will see you in January. Thanks all.
Thanks, Dale. Thanks, IACME. Really appreciate it.
Thanks, everyone.